Hey everyone, our project title is Experimental Modeling in Water Flooding. We're team number 12. My name is Ahmed Zigel.
Coleman Watson.
I'm Steve Maggio.
Bradley Doucette.
And our advisor is Bikash.
So here we're going to start with a review of our important concepts. First, I'm going to begin with mobility ratio. Mobility ratio is defined as the ratio of the mobility of displacing over the displaced fluids or injected over produced. And mobility is defined as the permeability over viscosity. So as we change our mobility ratio, we're changing which fluid is injected and which is produced. And changing mobility ratios also changes our aerial sweep efficiency. Our aerial sweep efficiency is the area swept over the total area, and this helps us to understand how much of the desired fluid can be recovered and how fast it can be recovered. A mobility ratio of less than 1, it produces a greater aerial sweep efficiency, and this is considered favorable because it produces more of the production fluids and a greater area swept. And then we have a mobility ratio of greater than 1. Although it is producing faster, it is unfavorable because it's a lower aerial sweep efficiency, and this results in residual oil saturation that is greater.
So another important concept is flood patterns. So we're going to be building an inverted 5-spot model, which is one of the most common due to the simple square geometry of it. So in a 5-spot, in an inverted 5-spot, we have one injection well to 4 production wells. Another benefit of building an inverted 5-spot model is in the reservoir mechanics lab here at LSU. We have a quarter 5-spot, as we're going to be building a full scale model 5-spot.
Project goals and objectives. First, successfully build inverted 5-spot model for experimental testing. Also, observe aerial sweep efficiency with changing mobility ratio. Also, observe water flooding effects in a sandstone core with specific permeability. Water flooding simulation to compare results with functioning model.
So our final goal next semester is going to be to build a functioning model so that it may be used for future experiments at LSU and in the reservoir mechanics laboratory.
So Bikash has given us a lot of good feedback. To determine what core we were using, we narrowed it down to sandstone, carbonate, and shale. Bikash told us that we should probably use sandstone because shale and carbonate have very low permeabilities, and because of the low permeability, it would take us between 24 to 48 hours to run an experiment, and also the low permeability will cause a high pressure in our model, and if the pressure becomes too high, then our model could crack. Also, Bikash told us while constructing our model that we should put rollers on the bottom of the model in order to make it mobile and just easier to transport. Obviously in the field, oil and water would be your fluids, but in a lab setting, using oil and water would be difficult to clean from the model. Therefore, we've decided to use oil-based liquids, which behave similar to oil. And for our time frame, Bikash told us that a lot of issues tend to arise whenever building models, so we should order our material immediately, and then once we get back from break, that we should begin building our model. And as you can see here, this is a picture of the quarter 5-spot model that they have in the reservoir mechanics lab. So you have injection into the core, and then it is being produced out from the other side. Since we are using an inverted 5-spot model, we will have an injection well in the middle, and then we will be producing from all 4 corners.
So our project management, we're going to have to purchase the material needed for model. We've been working on that. We're getting pretty close to getting that one taken care of. Lighting table platform, I'm going to be doing that. So the way I'm going to be building it and constructing it is I'm going to have 4x4 wood stumps, and I'm going to put a hardened wood platform on top, And I plan to cut a 20-inch by 20-inch square hole in the middle, and then place a glass sheet on top of the hole, and then I'm going to hook lights underneath to allow the lighting to pass through the glass so we can trace the advancement as we did in our reservoir mechanics. Bradley's going to be constructing the sandstone core.
So for the fluids in our model, we will be using Soltrol and naphtha. We will be alternating which one we are injecting and which one we are producing, and this will produce varying mobility ratios. And this is due to the fact that these fluids have different viscosities. The reasoning for choosing these two fluids is because they are miscible in all proportions, and this produces a constant effective permeability throughout the displacement process. And therefore, mobility ratio would just be the ratio of the viscosities. So then to inject these fluids into the into the core, we have tubing and injection and production valves. And then once the model is constructed, we will be troubleshooting to check for leaks and other problems that might occur. And once we know the model is fully functional, we will be testing the model. And once the model, time permitting, we will do water simulations to compare our data.
So this is the budget for our project. I'm in charge of finding the sandstone. I've been looking into purchasing an already pre-made sandstone core. I found a company called Berea Sandstone that makes cores. Their standard permeability for their cores would be 100 to 200 mil-Darcy, but they make cores with permeability of all ranges. So I've emailed them the dimensions of our core that we want and the permeability, and we're just waiting for a reply to receive a quote. Obviously, if the quote is too high, then we plan on meeting with Bakash and figuring out a way that we can construct our own core. We'll be using epoxy to coat the sandstone core, and that will be used because to prevent fluid leakage.
So as in the last slide, I'm going to be doing the lighting table. You can build a pretty cost-effective lighting table just using Lowe's and Home Depot. We're going to have our 5 pieces of wood, our 4 stumps, and our hardened wood on top. Then we got to have our glass. Just depending on the grade of glass, it's going to be $10 to $40 depending. And then we have our lighting. It's going to consist of our light bulbs and our light sockets.
So here we have the fluids, naphtha and Soltrol. We've contacted multiple companies on getting prices for our amounts we're looking for. However, we're still waiting on a quote from these companies. We also have the phenolic caps, which are $40 total. These are used to allow injection and production into the tubes and valves.
Miscellaneous, we've got tubing and valves. For tubing, it's 25 feet. The outer diameter is 1/8 of inch. The price is between $4 and $10 depending on the brand name. For the valves, we need 5 valves for production at the corners and 1 injection well at the center. For the inner diameter is 1/8 of inch, and the prices is between 15 and 20 depending on the brand name.
So next we would talk about the health and safety environment concerns. First, we'll be wearing gloves when dealing with epoxy and coating sand. This is because epoxy is a skin irritant. And then also we will be wearing protective eyewear throughout all times when constructing and testing the model. When constructing the model, we will be using wood saws, drills, and screws, and protective eyewear is necessary.
So this is our Gantt chart to help illustrate our time frame. So once we have all of our materials, we will begin by constructing our lighting table, and we will follow that by building our model, which we believe will take about 2 months. And then we will begin troubleshooting to fix any issues that may come up. And finally, we will end it by running our experiments and presenting our findings.
So some resources we have, our simulation, we plan to carry out next semester to compare our data. Reservoir Mechanics Lab has proved to be very beneficial. I was taking it this semester. We've really learned how to apply the model itself and what are the uses of it. And Vakash, we've utilized him. We plan to do that next semester as well. And here are our references. Thank you for your time.